In this video, we're going to look at the infimum of a nonempty set. Infimums are defined in the same kind of way that supremums are defined. So I want to actually start by looking at the definition of the sup of S. In the last video, we defined the sup of S as S is bounded above, and if P is inside R and it has these two properties, that P is an upper bound for S and that P is smaller than all other upper bounds of S, then P is called the sup. What I want to do is I literally want to modify this definition to get a definition for the infimum. The infimum is going to be the biggest thing that is smaller than all elements of S. So what we're going to do is we're going to change bounded above to being bounded below. And let me make my handwriting just a little bit better. And if I'm going to be having S bounded below, then I'm going to want to be looking at P being a lower bound. And I'm going to be comparing P to all other lower bounds. So this upper gets changed to the word lower. But if I'm comparing P to all lower bounds, then this inequality is also going to have to swap. In other words, the infimum is going to need to be bigger than or equal to all lower bounds. And then obviously we need to change the notation. And we're going to call P the infimum of S. So we write P equal inf S. This is usually pronounced as inf. So P is called the infimum of S when you have all of this stuff happening. And the infimum is really the greatest lower bound for set S. Now it turns out that since all we've done is swapped bounded above for bounded below and upper bounds for lower bounds, and this one inequality being changed to the appropriate natural direction, we get the same kind of number lines that we had for sups, except that they're kind of flipped upside down. In other words, if here is my number line and I put P here is the infimum of S, what that tells me is that all of the elements of S have to live over here. In other words, no element of S is bigger than P, because P is a lower bound. I also know that if I look at any lower bound, so these are lower bounds for S, then they are, any lower bound for S has to be less than or equal to P. So these are my lower bounds P. Lower bounds named B. But I also want to focus in on this part of the number line in particular. So let's redraw that number line. And let's see, we want to put P here. And I'm going to put a little delta ball. So this is a delta ball centered at P of radius delta. And what I want to notice is that if I look at this side of the delta ball, I know that since P itself is the inf of S, that P plus delta is not a lower bound of S. And so what that tells me is that there has to be some element, and it might be equal to P, some element of set S must lie inside the half-closed interval starting at P and running up to P plus delta. So running up to P plus delta. And here again, if P is not inside S, what that's going to tell me is that I'm going to have somebody inside this open interval between P and P plus delta. And if P is inside S, then P is going to be the minimum element of S. So let's look at those two cases as well. So if P is equal to the inf of S and P belongs to S, then when I look at my number line and I think about where P is inside S, and that means that I know that P is going to be the minimum element of S. So P will be inside S, and for every little s inside S, little s will be bigger than or equal to P. On the other hand, if P equals the infimum of S and P is not part of the set S, then our number line looks like this. Here is P again. And this time I know that P is not inside S. So when I look at this delta ball, and this endpoint of the delta ball is P plus delta, since P itself is not inside S, that means there has to exist a little s inside capital S such that little s belongs to this half of the delta ball. It belongs to the open interval between P and P plus delta. And I can do this for every delta bigger than 0. So this kind of a picture is going to be true for all deltas bigger than or equal to 0 when the infimum is not part of the set.